Stockmarr. I'm from Denmark, and I'm going to talk about a project I did together with Carsten Kirkeby and René Bødker on bluetongue and schmallenberg virus. In fact, this is a reanalysis of an earlier experiment, but this doesn't. Let's see. Bluetongue and schmallenberg viruses are viral diseases that affect ruminants. They are not zoonoses. They are not dangerous to people, but they do affect mainly sheep, cattle, and goats. The epidemiology is so that it has been endemic in Southern Europe and other parts of the world. But in 2006, the bluetongue virus strain 8 reached Northern Europe, and in 2007 we had the first case in Denmark. In 2012, the schmallenberg virus followed, and you can see the transmission routes as they are believed to be from this graph here. The point here is that these diseases are vector-borne. They are transmitted by biting midges, colecoides. In Southern Europe, this vector here is the one responsible, and this guy here is responsible in Africa, Asia, Australia, and also parts of Southern Europe. However, progression northwards was first actually ascribed to climate changes because the temperature was partly ascribed to big rising, but it has been realized now that there are new vectors, namely Pulicaris and Obsoletus, that can actually acquire and transmit the viruses. And that means that you place this virus in a completely new environment with lots of vectors to actually enter, and that gives a specific problem. The problem with bluetongue and schmallenberg is primarily, if not for ethical causes for the animals, then it is an economic problem. It has been estimated that if you had a similar outbreak as the one you had in Belgium in 2006 and 2007 in the UK, the cost would be about £485 million and 10,000 jobs. So it can have quite severe effects if it isn't really treated. And the problem is, first of all, that here you can see the outbreak that has come in the EU in 2008 and 2009. That there isn't really marked anything here is only because these are the EU outbreaks, and if you don't look for it, you don't register the outbreaks, so it's probably also there in the East. But it is so that we don't really have any treatment for these diseases here. So in order to contain the disease, we have quarantine. We have inoculation with live viruses. We do have BTV8 vaccines at the moment, but if you do inoculation with live viruses, you will have problem with the export markets for your dairy products and similar things. So people are sort of reluctant to do that. But the last thing you can do is actually to contain the vector, because if you don't have the vector to transmit the disease, you are indeed containing it, at least at a local scale. Now, we have done something on a national scale on how to sort of have alert systems for this, but what I'm going to tell you about is how you would do on a local scale, because the practical problem if you're a farmer and you have your animals and you wish to control or contain your risk of disease is sort of unclear at this moment here. So what we did was that we had an experimental field here where we had placed sheep in this end, and we placed 50 light traps in the field, and we ran all light traps in 4 nights per each week, and we emptied them and conserved the colecoides for later analysis. And then we did place some host animals during the nights. So these were the traps, these X's here. Down below here, there's a forest, which we'll come back to. And we then had all of these light traps, which attracts the midges. And they are then entered into a box here, which we simply emptied during the days of the experiment. So these are the data that I would like to talk to you about, to find out what are the conditions that sort of promotes that the biting midges are flying, that they are that they are a threat to the animals, and when can you be relatively safe that nothing is going to happen. So the animals were placed in the upper part of the field, and there's 260 sheep up here during the period. Now, in order to distinguish between what kind of effect will a single animal have compared to the 260 animals, we placed in some of the cat's nights single animals in cages in these positions on the field here. And what we were then looking for the effect of was indeed breeding size for the midges, the distance to the sheep, of course, doesn't matter, you guess so, the humidity, precipitation, and then a sheep transect, which is the line here, where we have the individual animals, which then emits far less scent than the 260 animals up here, and then of course the temperature and the wind speeds. Furthermore, we constructed a measure for wind breaks, because the biting midges, they have to rest at some point. When they fly out, they need a blood meal in order to continue their life cycle, but when they're not sort of looking for that, they're sitting around resting, and they need resting places. So what we did was that we look at the edge of the fields, there are some edges here, and we took the angle for the wind direction at the current time, and calculated the sign of this, the numeric sign of this wind direction, and divided it with the distance to the actual trap here, 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 or here, and then gather these 4 edges here as a measure of the wind breaks at the specific catch site. And we did a similar thing for the sheep scent, because one of the hypotheses is that when this midge flies, it moves out to find a target animal, it flies crosswind. And it flies crosswinds until it picks up a scent, and the moment it picks up a scent, it flies upwind in order to go in the direction from where the scent is. So we also use this line here as the borderline from the sheep up here, and looked at the direction of the wind. So how much scent is blown downwards on the field to the specific site there, and again discounted it with the distance from the sheeps. So these were the covariates. The data we then got was the number of female culicoides of the two species groups, Obsoletus and Pulicaris. They were counted in each light strap each day. There's kind of a problem with this, because there can be thousands of biting midges in each sample, and that meant that for each catch night we had to only count 50% of the trap catches, but at least we count them in a checkerboard pattern. But all in all, it resulted in that we had 16 catch nights, 530 trap catches, and about 15,000 Pulicaris, and 4,500 Obsoletus catches. So the original analysis was analyzed with a lattice model, where you took each of these positions here and conditioned with the neighbors, using this thing about that for spatial models you have conditional independence given the neighbors. We worked on a problem to solve the problem with missing values, but it is still very difficult when you do these things to actually interpret these dependencies spatially, and in particular also temporarily. Sorry, not temporary, but temporal. That is dependency in time. If you have an interest, you can look at Kirkeby et al. From 2013 for the details of this, but this is a short presentation, so I'll leave that out. However, there is this thing about the spatial and the temporal correlation, because you cannot use, when you need to analyze these kinds of data, you cannot do standard regression methods, because the data are correlated. They are not statistically independent. The problem is, of course, if you have a swarm of midges which are around a position here, there is a high likelihood that there is also a kind of a swarm in the neighbors. So if you have a high catch at one point, then there is a high probability that the neighboring traps will also catch a high number of midges. And therefore, you have to take this into account somehow. The further away in distance the traps are, the lesser this effect. But there's also one in the temporal dependency, because if you have a high catch in one trap, it likely means that there are many midges in this area, and they could also have been here yesterday, and they might be there tomorrow as well. And that means that you also have a dependency in time. And of course, the further away in time, the lesser the effect. And standard regression methods simply can't handle varying correlation in this way. Nevertheless, I decided that it could be fun to try to reanalyze these data and see what happens if we actually try to specify the covariance structure directly. So we specify directly how we would actually model these correlations. First of all, for spatial dependency that counts for clustering in space. This is a positive, or positive, depends on how you see it, many misses. And this is a negative cluster. And then there could be a temporal dependence, so this could be time in days. Here there's a lot of misses, then there's no one here, and then a lot again here. And then combine these two into a spatio-temporal dependency. So what we did was to specify a reference point. It doesn't really matter here because the effects would be independent of these here. And let x to be the catch at horizontal distance I, vertical distance j, and temporal distance, that is the difference in time, from the reference points. We log transform them and then model the correlation between these numbers by a parameter to the power of the Euclidean distance between the observational, or the catch sites, times another parameter to the power of the number of days that are between these catches. So if it is catches on the same day, this guy here will be 0, and this will be the only effect you'll see. If it is catches on the same site, but in different days, this guy here will be 0, and this is the only effect you will see. With that modeling, you can take and construct a matrix like this, which corresponds to the correlation of each of these individuals here, and model all of the observations as one big multivariate normal observation with a set of fixed effects that corresponds to all of the covariates I've been describing, structured in the x, and the effect parameters in the beta, and a covariance structure as described on the previous slide. So in principle, this is a standard model, but just with a very complicated structure over here, and definitely a non-linear model. Nevertheless, it does have a likelihood function, which looks on this form. It is a bit problematic actually to optimize it. It can be done in hand, but luckily I know a guy who is very skilled in developing software and which has worked over a couple of years to develop something which is called Template Model Builder. And if you are interested in missing, then the link is here for that kind of software. And that sort of solves this more or less immediate, even though that doesn't exist any closed form of the solution of this. It is still possible to derive the effects and the complex bands. So the effects are then shown here. These two columns here are for the obsoletus, which was those where we found about 5,000. And these are for the Polycaris group. And you can see here, first of all, we have specified some interaction things between the sheep scent and the distance to the sheep. It doesn't really appear significant. Neither does interaction between windbreaks and the sheep scent. The sheep scent itself actually is also insignificant. There is some sporadic significances here of windbreaks and sheep transect, but basically all of these here doesn't appear to have an effect. The rest, though, have strong significant effects, as you can see here. I should not go into details with the numbers here, but we can see some of the effects in a few slides. But the main thing here is that when we do this way of specifying the correlation and the variances, then from the original analysis we reveal some much higher spatial correlations, and in fact also a temporal correlation which is significant in this model but wasn't in the original one. And most importantly, then on the log scale here we have a much lesser residual variance. That means that we have a much more precise model when we do things in this way. So we do uncover both a temporal and some spatial correlations that are much higher than what is structured from the old way of looking at these data. So this is how it looks like. If you look at the meters apart, the whole field we were looking at on the long side, it was about 700 meters. You can see here that for the obsoletus group, the correlation sort of extends to the whole fields. It suggests that there is an external source of midges, because if they're there, they're sort of more or less over it all. While the correlation sort of disappears at about 100 and 150 meters for the Polycaris group. And since there's 50 meters between each of the catch sites, it means that you're dependent on your neighbor, perhaps a little more, not more than that. This here is the temporal correlation. How many days back in time do we have a correlation? And you can see here that it goes back 2, 3, or 4 days. Many of these 16 catch nights were weeks apart, so it is only a few days where you can actually expect to have these kinds of correlations, and it also means that there likely isn't any specific non-modeled things that have actually attracted the midges. So in order to say something about the effects, we didn't find any, or perhaps only limited effects of breeding size, windbreaks, the sheep sense, which we were actually hypothesizing about that really played a role. Neither the sheep transect, where we only had individual animals, they didn't really seem to have any effect compared to the 260 animals in the end of the field, and the specified interaction effects from the last slide weren't really significant either. However, here are some of the significant effects. This is the distance to the sheeps, and you can see here there is a nonlinear effect, so the effect is highest when you are close to the sheeps, of course, but actually there's also something if you are at the end of the field where there is something that attracts them in the forest area from the other side. The effect of the temperature is so that the midges, they need a temperature between, say, 14 and 18 degrees Celsius before they actually fly and go for their blood meal. If you are not in this temperature area here, it doesn't really seem like they are flying, and then they are simply sitting and waiting. This here is the effect of the wind. And actually, in order to fly and go for their blood meal, there has to be a certain amount of wind speed, because if there's no wind, they likely still have a problem in picking up whatever scent they need to have. So this is a bit surprising if you compare with that we couldn't find any effect of the actual sheep scent as we have modeled it. Nevertheless, the critical conditions where you could say that the midges are flying and they are moving towards the animals is humid conditions, 14 to 70 degrees Celsius, and moderate wind. However, there's also non-critical conditions. It's either if it's rainy, if it is turbulent, or if there's no wind. Then the midges are not flying, and you are not really running any risk. Also, the effects seems to be species independent. That means that the level of the effects are sort of more or less the same for each of the two species. And of course, this means that once you want to take action in a local area, you should, of course, look for the critical conditions. It's also so that the direct specification of these correlations, they do reveal a much higher spatiotemporal correlation than in the original analysis, and it does reduce the model error by a factor 2 to 3 on the log scale. And that means for the actual scale, it's quite a lot. So thank you for your attention. That's what I had to say.
Sticking to time. Got time for a couple of questions.
How did you measure sheep scent?
Oh, we didn't measure it. We parameterized it. We parameterized it with the angle to the. Let me just. Where do I get up? Page up. There it is. We parameterized it with. Oh, that was perhaps too much. No, it was there. There it is. We parameterized it with the distance to the sheeps multiplied with the wind speed and a factor that accounts for the wind direction. So if you have a wind speed or wind direction which is parallel with this line up here, there's absolutely no effect. And if it is perpendicular, you will have full effect. And then it is parameterized with this here, so the effect is sort of estimated from the data.
But you found a correlation with wind, but not with sheep scent. But the
Yeah.
sheep scent was parameterized from
Yeah,
the
so
wind.
the wind is the wind speed. So there is an effect of the wind speed that we did detect, and I should emphasize that the fact that we didn't see this effect doesn't mean that it isn't there. It's just that we were not able to detect it significantly.
But sorry to interrupt, I'm sorry. Like you say, like your classification is based upon this, what you said right now, the interference of wind and all. And lastly, you said like wind at all has got no effect. So how do you, what you can say, bang up on the fact
wind strength or wind speed did have an effect. What we couldn't make any effect of was the direction compared to where the sheep was. So whether it was blowing from that direction or from that direction or the other way didn't really matter, or we couldn't really detect any effect of it. Just the fact that it was windy meant something, and we also did detect that turbulence actually was a major contributing factor. If it's too turbulent, then the midges are not flying. Then they are sitting on the ground and waiting for better times.
Well, I have a similar question, but now I'm going for another question when I have the time. These animal diseases, which are outbreaks, they happen to be more frequent when you have animals of the same species in big groups together. And with the development of Africa, where we have a lot of interesting microbiology, and with the development we get bigger farms in Africa and also more animals on one spot in Africa. Is this a threat for world infectious in animal diseases?
Well, you could say that bluetongue has been endemic in Africa, as far as I know, for a number of years. So it's not something that is uncommon for them. The situation in Europe is that it is new, it is emerging in Europe. So that's why we are sort of looking at it here. But I mean, the effect is not going to be that different, I guess, tomorrow in Africa than it was yesterday, because this is not something where we have discussed changes over time in the disease. This is merely an attempt to get an idea about where are the transmitting vectors. So we are not discussing anything at all about the effects. Of course, if you have huge amount of scent, which we have up here, 260 compared to these here, it does have an effect that sort of overpowers the others. So my guess would be that if you have more and more animals, there would be more and more compact scent, and that would attract the midges more and more. That would be my guess. But we don't look into the consequences here on that, because I mean we haven't gotten that much in Europe to look at.
Okay. Is your analysis based mainly on regression models?
Oh, yeah, more or less, but still then not again, because we can't use regression models because all of these things about correlation in the data.
I mean, do you use structural equation modeling?
No, it's not structural equation modeling. It is a Gaussian model.
Bayesian networks, and now you can also use something called Markov-Blankes.
Yeah, but it's nothing of that kind. It is in fact a standard multivariate normal model where you specify a normal distribution and a variance-covariance matrix. For standard regression, here is a diagonal matrix which indicates that there's no dependence between these, and the difference here is that we have a complicated dependence structure, and that actually seems to solve the thing.
Okay, thank you. We'll move to the next speaker.